Hello everybody, welcome back to my channel, and in this video we're going to just revise the class 11th geography textbook for physical geography, the fundamentals of physical geography. So we'll first start with the chapters on climatology. Let's start with chapter 9, which is solar radiation, heat balance and temperature. So skip this much. Then Earth receives almost all of its energy from the sun. This Earth in turn radiates back to space the energy received from the sun. As a result, the Earth never warms up, nor does it get cooled over a period of time. Thus, the amount of heat received by different parts of the Earth is not same. This variation causes pressure differences in the atmosphere. This leads to transfer of heat from one region to the other by winds. So, the solar radiation. The Earth's surface receives most of its energy in short wavelengths. So, like the incoming rays from the sun are very high in energy. We knew the formula that E equals to hc by lambda, where h is the Planck's constant, lambda represents the wavelength, and c is the speed of light. So E is inversely of lambda. So since energy of sun, like the solar energy is very high energy, that is why it will thereby have short wavelength. So Earth's surface receives most of its energy in short wavelengths. The energy received by the Earth is known as the incoming solar radiation, in which in short is known as the insolation. As the Earth is a geoid resembling a sphere, the sun rays fall obliquely at the top of the atmosphere, and the Earth intercepts on a very small portion of the sun's energy. So, on an average, the Earth receives 1.94 calories per square meter per square centimeter per minute at the top of its atmosphere. The solar output received at the top of the atmosphere varies slightly in a year due to the variation in the distance between the Earth and the Sun. So the distance between the Sun and the Earth also has an effect on how much the sunlight enters Earth. Then, during its revolution around the Sun, the Earth is the farthest from the Sun on 4th of July, which is known as the aphelion position. So, like, if this is the axis of Earth and this is the Sun, so this very position is known as the perihelion, whereas if Earth is here at the farthest one, this position is known as aphelion. So 4th of July mostly is known as the aphelion. The position of the Earth is called aphelion. On 3rd of January, the Earth is nearest to the Sun. This position is called the perihelion. Therefore, the annual insolation received by the Earth on 3rd of January is slightly more than the amount received on 4th of July. So here we are talking about the parameter of distance. So, however, the effect of this variation in the solar output is masked by the other factors like distribution of land and the sea and the atmospheric circulation. Hence, this variation in the solar output does not have great effect on the daily weather changes on the surface of the Earth. So, although there is a distance factor, but this factor gets masked by different factors like atmospheric circulation, distribution of land and sea, all of that, and therefore the effect of this distance is very minimal in terms of the other factors if we consider them. So, the variability and insolation at the surface of the Earth. The amount and the intensity of insolation vary during day, in a season, and in a year. The factors that causes these variations in insolation are rotation of the Earth on its axis, the angle of inclination of the sun's rays, the length of the day, the transparency of the atmosphere. The length of the day basically depends also on the rotation of the Earth, the transparency of the atmosphere, then the configuration of land in terms of its aspect. The last two, however, have less influence. So, the fact that the Earth's axis makes an angle of 66.5 degrees with the plane of its orbit around the Sun has a greater influence on the amount of the insolation received at different latitudes. Note that the variations in the duration of the day at different latitudes. Okay. Second factor that determines the amount of insolation received is the angle of inclination of the rays. This depends on the latitude of a place. The higher the latitude, the less is the angle they make with the surface of the Earth, resulting in slant rays. So over here we have a table for the length of the day in hours and minutes on winter and summer solstice in the northern hemisphere. So here, uh, during December 22 and June 21, we're considering these two dates. And in December 22, at 0 degree at equator, both of these two solstices, like this is the winter solstice, this is the summer solstice. That the length of the day and night is same. So like 12 hours, length of day is 12 hours. So as you go up, the length of the day decreases during winter solstice. Whereas in summer solstice, as you go up, the length of the day increases. You could see over here it is 6 months for the countries or the places near to the Arctic Circle or beyond that. Then the higher the latitude, uh, the higher the latitude, the less is the angle they make with the surface of the Earth, resulting in slant sun rays. So here you can see, as you go up here, that there are slant sun rays. The area covered by the vertical rays is always less than the slant sun rays. If more area is covered, the energy gets distributed, and the net energy received per unit area decreases. So, like if this is the area and more sun rays and there is just one sun ray, so the energy gets distributed along that whole parcel of land. So if more area is covered, the energy gets distributed and the net energy received per unit area decreases. Moreover, the sand rays are required to pass through greater depth of the atmosphere, resulting in more absorption, scattering, and diffusion. Therefore, less energy. Then the passage of solar radiation through the atmosphere. The atmosphere is largely transparent to short wave solar radiation. The incoming solar radiation passes through the atmosphere before striking the Earth's surface. Within the troposphere, water vapor, ozone, and other gases absorb much of the near infrared radiation. So you might know that the tropospheric ozone is detrimental to climate. So like it also leads in climate change. So ozone at stratosphere prevents us from the UV rays, whereas the tropospheric ozone is a short-lived climate pollutant. So in the troposphere, water vapor, ozone, and other gases absorb much of the near infrared radiation. Very small suspended particles in the troposphere scatter visible spectrum both through space and towards the Earth's surface. This process adds color to the sky. So the blue color is because of the scattering of light. You might have read in the standard 6th, 7th in school. The red color of the rising and the setting sun and the blue color of the sky are the result of the scattering of light within the atmosphere. The spatial distribution of insolation at the Earth's surface. The insolation received at the surface varies from about 320 watts to about 720 watts per meter square in the poles. So, like more insolation is received in the tropics, whereas less insolation is received in the poles. Maximum insolation is received at the subtropical deserts, where the cloudiness is least. So, more cloud means more moisture. So, therefore, less of sunlight. Clouds basically reflect it. Equator receives comparatively less insolation than the tropics because of the tilt. Generally, at the same latitude, the insolation is more over the continents than over the oceans because land heats are faster than the oceans. Land heats are faster than water. In winter, the middle and the high latitudes receive less radiation than in summer. So, with the spatial distribution of the insolation at the Earth's surface, what we could infer is that equator basically receives less rainfall than the tropics, and the same latitude. At the same latitude, the insolation is more over the continent than over the oceans, and insolation decreases as we move towards the poles. Then the heating and cooling of the atmosphere. The different ways of heating and cooling of the atmosphere. The Earth, after being heated by insolation, transmits the heat to the atmospheric layers near to the Earth in long waveform. So, like the income, if this is the Earth's surface, the incoming are short wave, whereas the outgoing or the terrestrial radiations are the long wave. So, Earth, after being reheated by insolation, transmits the heat to the atmospheric layers near to the Earth in long wave form. The air in contact with the land gets heated slowly, and the upper layers in contact with the lower layers also get heated. This process is called as conduction. Conduction takes place when two bodies of unequal temperature are in contact with one another. There is a flow of energy from the warmer to the cooler. So, because of the long waveform heat transmitted by the Earth's surface, the air parcel near to the surface gets heated, and the air parcel which is like near to this air parcel 1, that is this one v1, this one is 2, so the air parcel 2 also gets heated. This process is known as conduction. So here the energy is transferred from the warmer to the cooler surface. The transfer of heat continues until the two bodies attain the same temperature or the contact is broken. Conduction is important in heating the lower layers of the atmosphere. The air in contact with the earth rises vertically on heating in the form of currents and further transmits the heat of the atmosphere. This process of vertical heating of the atmosphere is known as convection. So we have read about two processes. One is conduction, the other is convection. When there is vertical heating, so the air rises up after getting heated. This process is known as convection. The convective transfer of energy is confined only to the troposphere. The transfer of heat through horizontal movements of air is called advection. So we have read about conduction, convection, and advection. Conduction is like these are two bodies who have a contact over here. So if you heat, like there is a source of heat, it would get transferred. Then in convection, a body gets heated and rises vertically on heating. Then in advection, the transfer of heat is through the horizontal movement of air. So horizontal movement of air is relatively more important than the vertical movement. In middle latitudes, most of the diurnal day and night variation in daily weather are caused by the advection alone. So in the middle latitudes, the diurnal ranges of temperature is because of advection alone. In tropical regions, particularly in northern India, during summer season, local which called Lu is the outcome of the advection process. And then the terrestrial radiation. The insolation received by the Earth is in short waveforms and heats up its surface. The Earth, after being heated itself, becomes a radiating body, and it radiates energy to the atmosphere in long waveform. So like less energy but high wavelength. So long waveform. This energy heats up the atmosphere from below. This process is known as terrestrial radiation. The long wave radiation is absorbed by the atmosphere, particularly by carbon dioxide and other greenhouse gases. Thus, the atmosphere is indirectly heated by the Earth's radiation. When the atmosphere in turn radiates and transmits heat to the space, finally the amount of heat received from the sun is returned to the space, thereby maintaining constant temperature at the Earth's surface and in the atmosphere. This can also be like an analogy can also be given by homeostasis or trying to maintain an equilibrium. So the amount of heat received from the sun is returned to the space, thereby maintaining a constant temperature at the Earth's surface and in the atmosphere. So there is a heat budget of the planet Earth. This is the heat budget. We have the short wave solar radiation, which is the incoming solar energy, and then the long wave Earth radiation, which is the outgoing or long form terrestrial radiation. So for the incoming, the total radiation, we have the total radiation which is 100%, out of which clouds reflect 27 parts of it. Then 6% is like scattered to the space, 2% is reflected by the Earth's surface itself. Then out of the scattered radiation, there are two parts. One is scattered to space, one is scattered to the one is deflected towards the Earth's surface. So out of that, 17% is absorbed by the Earth, 34% is absorbed is also absorbed by the Earth via direct like via direct by the radiations travel directly. Also, 40% is absorbed by the atmosphere. So, for the long wave Earth radiation, around 17% is directly radiated to space from the Earth, 48% is radiated to space from by the atmosphere. Then all of this. So, overall, the total heat budget is balanced, and thereby this helps us in sustaining life on the planet Earth. The Earth as a whole does not accumulate or lose heat; it maintains a temperature. This can happen only if the amount of heat received in the form of insolation equals the amount lost by the Earth through terrestrial radiation. So, incoming equals to outgoing. That's the basic concept, basically. The percentage of insolation received at the top of the atmosphere as 100%. While passing through the atmosphere, some amount of energy is reflected, scattered, and absorbed. Only the remaining part reaches the Earth's surface. Roughly 35 units are reflected back to the space even before reaching the Earth's surface. Of these, 27 units are reflected back from the top of the clouds, 2 units from the snow and ice covered surfaces of the Earth. The reflected amount of radiation is called the albedo of the Earth. So, albedo is basically a term in order to denote the reflection. So, the reflected amount of radiation is called the albedo of the Earth. So, the snows, ice sheets have most albedo. The lowest albedo is of the uh, bitumen roads, the black tar roads. The remaining 65 units are absorbed, 14 units uh, within the atmosphere, and 51 units by the Earth's surface. The Earth radiates back 51 units in the form of terrestrial radiation. Of these, 70 units are radiated to space directly, and the remaining 34 units are absorbed by the atmosphere. 48 units absorbed by the atmosphere are also radiated back into space. Thus, the total radiation returning from the Earth and atmosphere respectively is 65 units, which balances the total of 65 units received from the Sun. This is termed the heat budget or the heat balance of the Earth. This explains why Earth neither warms uh, up nor cools down despite the huge transfer of heat that takes place. But this process is basically disrupted by the greenhouse gases, which leads to the greenhouse effect, where there is more heat accumulated inside the earth, where the heat is more trapped, and that heat could not escape, thereby just disbalancing the heat budget because of anthropogenic causes. Then the variation in the net heat budget at the Earth's surface. There are variations in the amount of radiation received at the Earth's surface. Some part of the Earth has surplus radiation balance, while the other part has deficit. So let's see the latitudinal variation in the net radiation balance of the Earth. There is a surplus of net radiation balance between 14 degrees north and south. So here you could see that there is this surplus between 40 degrees north and 40 degrees south, whereas there is a deficit between 40 degrees and 70 degrees. And so the region near the pole have a deficit. So here they have more solar radiation, whereas in these regions near the poles is a deficit because the solar radiation is less. As we also studied in terms of the variation due to the latitudes, that as you move up towards the latitudes, the amount of insolation is decreased. Surplus heat energy from the tropics is redistributed polewards, and as a result, the tropics do not get progressively heated up due to the accumulation of excess heat. or the high latitudes get permanently frozen due to the axis deficit. So this is like nature's true artistic approach. So like as you could see, so from 40-degree north to 40-degree south, there's a surplus, like more amount of sunlight is received, whereas near the poles there's a deficit, less insulations. So it is not a case that these areas will remain totally frozen and these areas will get totally heated up. Now the uh, like redistribution takes place. The surplus heat is basically redistributed polewards. It goes polewards, therefore maintaining the balance, maintaining Earth's temperature overall. And this is done because of the atmospheric circulations. Then the temperature. The interaction of insolation with the atmosphere and the Earth's surface creates heat, which is measured in terms of temperature. While heat represents the molecular movement of particle substance, comprising a substance, the temperature is the measurement in degrees of how hot or cold a thing or a place is. So heat and temperature have been differentiated over here. Heat basically represents the molecular movement of particles which comprise a substance, whereas temperature is just a measurement of how hot or cold a thing is. Then factors controlling temperature distribution. The temperature of air at any place is influenced by the latitude of the place, the altitude of the place, the distance from the sea, the air mass circulation, the presence of warm and cold ocean currents, also the local aspects. So, in terms of the latitude, the temperature of a place depends on the insolation received. It has been explained earlier that the insolation varies according to the latitude, hence temperature also varies accordingly. So, as we move up towards the latitude, insolation decreases. Therefore, the temperature also decreases as we move up towards the latitude. Then, in terms of the altitude, the atmosphere is indirectly heated by terrestrial radiation from below. Therefore, the places near the sea level record higher temperature. So, this high temperature near the places near to the sea level is because of the terrestrial radiation, which is indirectly heating up the atmosphere due to conduction. Therefore, the places near the sea level record high temperatures than the places situated at higher elevations. In other words, the temperature generally decreases with increasing height. The rate of decrease of the temperature with height is termed as normal lapse rate. So, normal lapse rate is basically a measure or a rate of decrease in temperature with height. So, it is 6.5 degrees Celsius per 1000 meters, 6.5 degrees Celsius per kilometer. At this rate, the temperature decreases. So with every 1 kilometer height you travel towards the vertical side, the temperature decreases by 6.5 degrees Celsius. So distance from the sea also matters. Another factor that influences the temperature is the location of a place with respect to the sea. Compared to land, sea gets heated slowly and loses heat slowly. Land heats up and cools down quickly. Therefore, the variation in temperature over the sea is less compared to the land. Like this can also be said as the moderate effect. The places situated near the sea come under the moderating influence of the sea and land breezes which moderate the temperature. The temperature is never too hot or never too cold. So there is a moderating influence of the sea and the land breezes. So like uh, never going into the extreme sides. The air mass and the ocean currents. Like the land and sea breeze, the passage of air mass also affects temperature. The places which come under the influence of warm air mass experience high temperature, and the places that come under the influence of the cold air mass experience low temperature. Similarly, the places located on the coast where the warm ocean currents flow record higher temperature than the places located on the coast where the cold ocean currents flow. So, let's assume this has to be the coast of Peru. Here there is the Humboldt current, and since this is a cold current, this area becomes a desert, and which is the Atacama Desert, and is like so. This is located on the coast where the warm ocean currents flow, record high temperature, where the places located on the coast where the cold ocean flow require show cooler temperatures, like lesser compared to the places with warm ocean currents. Then distribution of temperature. The global distribution of temperature can be well understood by studying the temperature distribution in January and July. The temperature maps with the help distribution is generally shown on the map with the help of isotherms. So isotherms are basically joining two places which have the same temperature. So isotherms are lines joining places having equal temperatures. In general, the effect of the latitude and temperature is well pronounced on the map as the isotherms are generally parallel to the latitude. The deviation from this general trend is more pronounced in January than in July, especially in the northern hemisphere. So here we have this temperature distribution. These lines are basically the isotherms. So we have to keep in mind one fact that land heats up or cools down faster than sea. So if here this is 20 degrees as we move upwards. So this is in the month of January. So as we move upwards, the temperature should decrease. Okay. So here this is 20, then here this will be 10. This will be 0 degrees. Whereas in the land, in terms of the sea, this will change. Yeah, we could also assume this part where there is a clear difference between land and sea here. So over here, see this is 0 degrees. This is 0 degrees on the land. As you move downwards, the temperature should increase. So here it is increasing in 20 degrees and then 10 degrees, then 20 degrees. Whereas in the sea, there is no contrasting effect as such because the land heats up faster than the sea. I guess I'm missing some point because there was a very key point related to this. In the northern hemisphere, the land surface is much larger than the southern hemisphere. Hence, the effect of land mass on the ocean currents are well pronounced. In January, the isotherms deviate to the north over the ocean and to the south over the continent. Isotherms deviate to the north over the ocean and to the south over the continent. This can be seen on the North Atlantic Ocean. So, in January, the isotherms deviate towards the north over the oceans, whereas deviate towards the south over the continent. This can be seen on the North Atlantic Ocean. Presence of the warm ocean currents, Gulf Stream, and North Atlantic Drift make the Northern Atlantic Ocean warmer, and the isotherms bend towards the north. Over the land, the temperature decreases sharply, and the isotherms bend towards the south of the Europe. So here isotherms bends towards the south of the Europe, whereas in the North Atlantic Ocean we could see may bend towards the north. They are like bending towards the north over the ocean, whereas they are bending towards the south of the Europe over here over the land. So in January, basically the over the continents, the isotherms shift towards the south, whereas over the oceans they shift northwards. It is much pronounced in the Siberian plain. The mean January temperature along the 60 degree east latitude is minus 20 degrees Celsius, both at 80-degree north and 50-degree north latitude. So here, the mean monthly temperature for January is over 27 degrees Celsius in equatorial oceans. Sorry, the mean monthly temperature for January is over 27 degrees Celsius in equatorial oceans, over 24 degrees Celsius in the tropics, and 2 degrees Celsius to 0 degrees Celsius in the middle latitudes, and minus 18 degrees Celsius to minus 48 degrees Celsius in the Eurasian continental interior. So over here, this region basically. So here we have this distribution surface. So you could directly see that if we compare both of these maps. So over the uh, lands, over these lands, if this is the isotherm of 20 degrees Celsius, the isotherm bends southwards. Like it has come over here. This one has come over here. So it is bending south as we move in January. Whereas the over the oceans, if this was the 10-degree Celsius isotherm, this 10-degree isotherm has turned southwards. 20-degree has also turned southwards. So over here, this is 20-degree one. Then this is the distribution or the range of temperature between January and July. You see over here. So you can see there are more variations in the northern hemisphere because of more land, whereas in the southern hemisphere there are not much variations. So southern hemisphere we can also study over here. As we go to January, over the land, the isotherm is moving southwards, whereas over the ocean it is bending towards the north. So the effect of the ocean is well pronounced in the southern hemisphere. Here the isotherms are more or less parallel to the latitudes and the variation in temperature is more gradual than in the northern hemisphere. The isotherms of 20 degrees Celsius, 10 degree and 0 degree run parallel to 35 degrees south, 35 degrees south and 60 degrees south latitudes respectively. In July, the isotherms generally run parallel to the latitude. The equatorial oceans record warmer temperatures more than 27 degrees Celsius. Over the land, more than 30 degrees Celsius is noticed in the subtropical continental region of Asia. So this basically is a feature of India. Then along the 40-degree north runs the isotherm of 10 degrees Celsius and along the 40 degrees south temperature of 10 degrees Celsius. The highest range of temperature is more than 60 degrees Celsius over the northeastern part of Eurasian continent. So the highest range of temperature is more than 60 degrees Celsius over the northeastern part of the Eurasian continent. This is due to continentality. The least range of temperature is 3 degrees Celsius is found between 20 degrees south and 10 degrees north. So over the northeastern part of the Eurasian continent, there is a high range of temperature because of the effect of continentality. So we finally finished this chapter. So over here, the sun is directly overhead at noon on 21st June. Summer solstice at. So we also have this question over here, like in which of the following cities are the days the longest? So we've read earlier that as we move up towards, like as we go higher towards the altitude side, the length of the day, as we move higher towards the latitude. So in the northern hemisphere, the length of the day basically increases. So in all of these, Chandigarh is more in terms of the latitude, is on a higher latitude. So therefore, Chandigarh, the atmosphere is mainly heated due to the short wave solar radiation. And then the match the following. So moving towards chapter 8 basically. So the composition and structure of the atmosphere. So the composition and structure of the atmosphere. These are the permanent gases of the atmosphere. We need to remember NOARC, night, sorry, N capital O, not smaller. So nitrogen, oxygen, argon, and carbon dioxide. These are the major components of the Earth's atmosphere. So you can see carbon dioxide is just 0.036%, but because of the greenhouse effects, the levels of the carbon dioxide in the atmosphere keeps on increasing. So atmosphere is composed of gases, water vapors, and dust particles. The proportion of gas changes in the higher layers of the atmosphere in such a way that the oxygen will be almost in negligible quantity at the height of 120 kilometers. Similarly, carbon dioxide and water vapors are found only up to 90 kilometers from the surface of the Earth. So, about these gases, carbon dioxide is meteorologically a very important gas as it is transparent to the incoming solar radiation but opaque to the outgoing terrestrial radiation. It absorbs a part of the terrestrial radiation and reflects back some part of it towards the Earth's surface. It is largely responsible for the greenhouse effect. The volume of other gases is constant, but the volume of carbon dioxide has been rising in the past few decades mainly because of the burning of the fossil fuels. This has also increased the temperature of the air. Ozone is another important component of the atmosphere found between 10 to 50 kilometers above the Earth's surface and acts as a filter and absorbs the ultraviolet rays radiating from the sun and prevents them from reaching the surface of the Earth. Water vapor. There was a question from water vapor in 2024. Water vapor is also a variable gas in the atmosphere which decreases with altitude. In warm and wet tropics, it may account for 4% of the air volume, while in the dry and cold areas of the desert and polar regions, it may be less than 12% of the air. Water vapor also decreases from equator towards the poles, so it is like the amount of water vapor is more in the equators, whereas it keeps on decreasing as we move polewards. It also absorbs parts of the insulation from the earth and preserves the earth's radiated heat. So this is also uh, one of the greenhouse gases. It thus acts like a blanket, allowing the earth neither to become too cold nor too hot. It absorbs the part of the insolation from the sun and preserves the earth's radiated heat. It thus acts as a blanket, allowing the earth neither to become too hot nor too cold. Water vapor also contributes to the stability and stability of the air. This is why water is truly essential for the life on the earth because it acts as a blanket, allowing the earth neither to become too cold nor become too hot. The dust particles. Atmosphere has a sufficient capacity to keep small dust particles which may originate from different sources and include sea salts, fine soil, smoke soot, uh, ash, pollen, dust, and disintegrated particles of meteors. Dust particles are generally concentrated in the lower layers of the atmosphere, yet convectional air currents may transport them to great heights. The higher concentration of dust particles is found in subtropics. The high concentration of dust particles is found in the subtropical and temperate regions due to the dry winds in comparison to the equatorial and polar regions. The dust particles, the more amount of dust particles is found in the subtropical and temperate regions because of the dry winds in comparison to the equatorial and polar regions. Dust and salt particles act as hygroscopic nuclei around which water vapor condenses to produce clouds. This is why in the regions of subtropical regions and temperate regions there is rainfall, more rainfall. Then the structure of the atmosphere. The atmosphere consists of different layers with varying density. and temperature. Density is highest near the surface of the Earth and decreases with the increasing altitude. The column of atmosphere divided into five different layers depending upon the temperature condition. They are troposphere, stratosphere, mesosphere, then the ionosphere, which is within the thermosphere, and then the exosphere. Exo means out, so beyond. The troposphere is the lowermost layer of the atmosphere. Its average height is 13 kilometers and extends roughly to a height of 8 kilometers near the poles and about 18 kilometers at the equator. So troposphere, if this is the Earth, so the troposphere is more towards the equators than towards the poles. So 18 kilometers at the equator, whereas 8 kilometers near the poles. The thickness of the troposphere is greatest to the equator because heat is transported to greater heights by strong convectional currents. This layer contains dust particles and water vapor. All changes in climate and weather take place in this layer within these 8 to 18 kilometers. 8 kilometers in the poles and 18 kilometers at the equator. So all the changes in climate and weather take place in this layer. The temperature in this layer decreases at the rate of 1 degree Celsius for every 165 meters of height. This is the most important layer for all the biological activities. So here you could see as we move like altitudinally upwards, the temperature basically decreases in the troposphere. Then this is the transition zone, the tropopause. The zone separating the troposphere from the stratosphere is known as the tropopause. The transition zone basically, the air temperature of the tropopause is about minus 80 degrees over the equator and about minus 45 degrees over the poles. Temperature here is nearly constant, hence it is called the tropopause. So temperature is nearly constant, that is why it is called the tropopause. The stratosphere is found above the troposphere, extends up to a height of 50 kilometers. One important feature of the stratosphere is that it contains the ozone layer. This layer absorbs ultraviolet radiations and shields life on the Earth from intense harmful forms of energy. After the stratosphere, we have the mesosphere. Mesosphere lies above the stratosphere, which extends up to a height of 80 kilometers. In this layer, once again, temperature starts decreasing with the increase in altitude and reaches up to minus 100 degrees Celsius at the height of 80 kilometers. The upper limit of mesosphere is known as the mesopause. The ionosphere is located between 80 and 400 kilometers above the mesosphere. It contains electrically charged particles known as the ions and hence it is known as the ionosphere. Radio waves transmitted from Earth are reflected back to the Earth by this layer. Temperature here starts increasing with height. The upper layer of the atmosphere above is uh, the uppermost layer of the atmosphere above the ionosphere is known as the exosphere. This is the highest layer. Very little is known about it. Whatever contents are there, they are extremely rarefied in this layer and it gradually merges into the outer space. Although all the layers of the atmosphere must face a sizing influence on us, geographers are concerned with the first two layers of the atmosphere, which are the troposphere as well as the stratosphere. The main elements of atmosphere which are subject to change and which influence human life on Earth are temperature, pressure, winds, humidity, cloud, and precipitation. So over here in this graph, we could see that as we move towards, as we climb up the altitude, the temperature decreases in the troposphere. Then in the tropopause, it becomes nearly constant, and then in the stratosphere, it decreases. Sorry, it increases again. This increase in temperature can be attributed to the effect of the ozone, which basically absorbs, or which basically plays a crucial role in absorbing the ultraviolet radiations, which are very harmful to Earth, to us and towards the Earth. So therefore, this absorption leads to the increase in temperature in the stratosphere. Then as we move upwards, again the temperature starts to decline. we reach a zone known as the ionosphere, which also reflects back the radio waves, and because of it being electrically charged, then there is further increase also because of the other uh, planetary situations as well. So temperature decreases in the troposphere, whereas it increases in the stratosphere, and it again decreases in the mesosphere, and then so it's a zigzag curve. Decrease, then increase, then decrease, then increase, like this. So we have completed chapter 8. We have the following gases contribute major portion. So we have read NOARC, nitrogen, oxygen, argon, and carbon. These are the four main components. Nitrogen around 78%. Then atmospheric layer important for the human beings as well as for all the biological activity is the troposphere. Sea salt, pollen, ash, these are all associated with dust particles. Oxygen gas is negligible quantity at the height of 120, I guess. Yeah, at the height of 120 kilometers. Which one of the following gas is transparent to the incoming solar radiation and opaque to the outgoing terrestrial radiation? This is carbon dioxide. So it is transparent to the incoming solar radiation, whereas opaque to the outgoing terrestrial radiation. Let's just read once again about the water vapor because this was asked last year. So it decreases with altitude, it decreases with latitude as well. It absorbs part of the insolation from the sun and preserves the Earth's radiated heat, thus acting like a blanket. Therefore, water vapor also contributes to stability and instability in the air. So, if we have finally completed two chapters, moving to chapter 10. So, chapter 10 is about the atmospheric circulation and the weather systems. So, the air expands when heated and gets compressed when cooled. This results in variations in the atmospheric pressure. The result is that it causes the movement of air from high pressure to low pressure, setting the air in motion. Atmospheric pressure also determines when the air will rise or sink. The wind redistributes the heat and moisture across the planet, thereby maintaining a constant temperature for the planet as a whole. So, because of the redistribution of the heat by the wind across the planet, the constant temperature for the planet as a whole is maintained. The vertical rising of the moist air cools it down to form the clouds and bring precipitation. So, the atmospheric pressure. The weight of the column of the air contained in the unit area from the mean sea level. So, pressure is basically force exerted per unit area. So, in terms of physics, it is force exerted per unit area. So, here, what we mean is the weight of the column of air contained in the unit area from the mean sea level to the top of the atmosphere is known as the atmospheric pressure. So, the pressure exerted by the atmosphere on a unit area of land. The atmospheric pressure is expressed in units of MB and pascals. The widely used unit is kilopascals, written as HPA. At sea level, the average atmospheric pressure is 1013.2 HPA. Due to gravity, the air at the surface is denser and hence has high pressure. So at the surface, the air is more dense, therefore high pressure because density basically equals to mass per unit volume because it is exerting more mass. Therefore, since the exertion of more mass, there would be more pressure. Also, you could derive it as since density equals to mass upon volume, density is greater. That means mass is greater. So, if mass is greater, then P equals to ma by area, where this m is basically the mass. So if mass is high, the pressure is also high. So pressure is directly related to the density. As the pressure is measured with the help of a mercury barometer or the aneroid barometer, the pressure decreases with height. So as the height increases, the pressure decreases. So as you go at higher elevations, the air pressure basically decreases. At any elevation, it varies from place to place, and its variation is the primary cause of air motion. That is, wind which moves from high pressure areas to low pressure areas. Then the vertical variation of pressure. In the lower atmosphere, the pressure decreases rapidly with height. The decrease amounts to about 1 MB for MB 1 MB. Now I remember MB is basically millibar. For the decrease amounts to about 1 MB for each 10-meter increase in the elevation. It does not always decrease at the same rate. So these are the standard pressure and temperature at selected levels. So you could see as we move, like in altitudinally, we move away from the sea level. The temperature decreases as well as the pressure decreases. This is in terms of the altitude. The vertical pressure gradient force is much larger than that of the horizontal pressure gradient, but it is generally balanced by a nearly equal but opposite gravitational force. So if this is the vertical pressure gradient force, so what pressure gradient force is basically the gradient is basically the difference between the pressures between two different areas. So if there is this vertical pressure gradient force, there is an equal and opposite gravitational force which is balancing it. Hence, we do not experience strong upward winds. So the horizontal distribution of pressure. Small differences in pressure are highly significant in terms of the wind direction and velocity. So here these lines basically represent isobars. Iso means same, bar represents for the pressure, so same. So these are just connecting areas of or locations of the same pressure. The small differences in pressure and highly significant in terms of the wind direction and velocity. Horizontal distribution of pressure is studied by drawing isobars at constant levels. Isobars are lines connecting places having equal pressure. In order to eliminate the effect of altitude on pressure, it is measured at a station after being reduced to sea level for purposes of comparison. The sea level pressure distribution is shown on the weather maps. Low pressure system is enclosed by one or more isobars with the lowest pressure at the center. So this is the lowest pressure. This is enclosed by two isobars, and this one also surrounding somewhat. This is the innermost pressure isobar circle. It has the lowest pressure. So low pressure system is enclosed by one or more isobars with the lowest pressure in the center. High pressure system is also enclosed by one or more isobars with the highest pressure in the center. So this over here you can see this is the high pressure system. This right here is the low pressure system. The world distribution of sea level pressure. The world distribution of sea level pressure in January and July has been shown. Near the equator, the sea level pressure is low and the area is known as equatorial low. So over here, the sea level pressure is low. This is why it is known as the equatorial low. And over here, the ITC, the intertropical convergence zone, appears. Along 30° north and 30° south are found the high pressure areas known as the subtropical highs. The subtropical highs or the subtropical high pressure belts. Further polewards around 60° north and 60° south, again there is low pressure belts, termed as subpolar low. Near the poles, the pressure is high and it is known as the polar high. So if I just draw an earth over here, yes, it's a very small earth. Anyways, if this is the earth, this is the equator. To the equator, this is the this is the poles which have highs, then 30 degrees, then 60 degrees, 30, 60. So this has lows, subpolar low, this are subtropical high, and this area, basically this one, is the intertropical convergence zone, which is the equatorial low, 0 to 5 degrees Celsius. These pressure belts are not permanent. So you could see these keep on changing from, we have two like representations, one for January and one for July. You could see the pressure belts are changing. So here this is high, but here now it has become low. In the month of January, this region experiences a high pressure belt, whereas in the month of July it experiences low pressure. So air has to travel from high pressure to low pressure. So over here air will travel like this, whereas in this one air will travel from high to low like this. So these pressure belts are not permanent in nature. They oscillate with the apparent movement of the sun. In the northern hemisphere in winter, they move southwards, and in summer, northwards. So in the northern hemisphere, in the winter, they move southwards. Yeah, so these are moving southwards over here in the winter, whereas they move northwards in the summer. We've also read about the temperatures. So in the northern hemisphere, in January, in winter, in the continents, the isotherms basically shift southwards, whereas in the oceans, the isotherms shift northwards in winter, basically in January. January is also the uh, perihelion position. So in the northern hemisphere in winter they move southwards, and in summer they move northwards. The forces affecting the velocity and direction of the wind. The air in motion is called wind. The wind blows from high pressure to low pressure. The wind at the surface experiences friction. In addition, the rotation of the earth also affects the wind movements. The force exerted by the rotation of the earth is known as the Coriolis force. Thus, the horizontal winds near the earth's surface respond to the combined effect of three major forces, which are pressure gradient force, frictional force, and the Coriolis force. So Coriolis force is basically the force exerted because of the rotation of the earth. So three major forces. First is the pressure gradient force, then the force of friction, and then the Coriolis force. These basically influence the horizontal winds near the Earth's surface. In addition, the gravitational force acts downwards. Then this is the pressure gradient force. The differences in atmospheric pressure reduces a force. The rate of change of pressure with respect to the distance is the pressure gradient. So the rate of change of pressure with respect to the distance. The pressure gradient is strong when the isobars are close to each other and is weak when the isobars are apart. So if this is an isobar, pressure gradient over here, if this is distance 1 and over here this is distance 1 and over here this is distance 2. Since distance 2 is greater than distance 1, therefore pressure gradient force over here distance 2 is less. The more closer the isobars are, the stronger is the pressure gradient force. Because here the distance needs to be less. PGF is equal to del P by D. Lesser the distance, more the pressure gradient force. So the isobars needs to be closer to each other for greater pressure difference. So for greater pressure gradient force. Then the frictional force. It affects the speed of the winds. It is greatest at the surface, obviously because of different objects it encounters, and its influence generally extends up to an elevation of 1 to 3 kilometers. Over the sea surface, the friction is minimal. Then comes the Coriolis force. The rotation of the Earth about its axis It fixes the direction of the winds. The force is called the Coriolis force after the French physicist who described it in 1844. It deflects the wind to the right direction in the northern hemisphere. So, and then because of the so if this is the Earth, because of its rotation over its axis in the northern hemisphere, the things will be deflected in the right direction towards their right, and the southern towards their left. It deflects the winds to the right direction in the northern hemisphere and to the left in the southern hemisphere. Deflection is more when the wind velocity is high. Coriolis force is directly proportional to the angle of the latitude. So this Coriolis force is basically proportional towards the angle of latitude, also to the wind velocity. The more the wind velocity, more is the deflection. It is maximum at the poles and is absent on the equator. This Coriolis force is absent at the equator, max at the poles, and we've read about the Coriolis force being directly proportional to the wind velocity. More the wind velocity, more is the deflection. It is also directly proportional to the angle of latitude. Coriolis force acts perpendicular to the pressure gradient force. So this is the pressure gradient force. Coriolis force will act perpendicularly, like at a 90-degree angle. The pressure gradient force is perpendicular to an isobar. So if this is the isobar, this is the pressure gradient force. This is the Coriolis force. The higher the pressure gradient force, the more is the velocity of the wind. The pressure gradient force, also the wind velocity, and larger is the deflection in the direction of the wind. So we've read about the Coriolis force, which acts perpendicular to the pressure gradient force. The pressure gradient force is perpendicular to an isobar. The higher the pressure gradient force, the more is the velocity of the wind, and the larger is the deflection in the direction of the wind. As a result of these forces operating perpendicular to each other, in the low pressure areas, wind blows around it. Because of this, the resultant will blow around it. So for two vectors basically which have motion and have a direction, which have speed and direction. So therefore, the resultant will move around it. Resultant is in terms of physics, resultant is this 45 degrees. As a result of these two forces operating perpendicular to each other, the low pressure areas where the Coriolis low pressure areas where the isobars have less pressure, the wind blows around it. At equator, the Coriolis force is zero and the wind blows perpendicular to the isobar because only the pressure gradient force takes place. Like it is the only effect which takes place because in the equator the Coriolis force is absent. The low pressure gets filled instead of getting intensified. That is the reason why tropical cyclones are not formed near the equator. So at the equator, the Coriolis force is zero and the wind blows perpendicular to the isobars. The low pressure gets filled instead of getting intensified. That is why tropical cyclones are not formed near the equator. So if this is the pressure gradient force, this is the isobar, this is the Coriolis force. In the equator, since there is no Coriolis force over here, just the pressure gradient force will come into effect and the wind blows perpendicular to the isobar. The low pressure over here doesn't get intensified and is just eventually filled. This is the reason why tropical cyclones are not formed near the equator. In low pressure areas, the wind blows around it. The higher the pressure gradient was, the more is the velocity of the wind, and the larger is the deflection in the direction of the wind. So the pressure and the wind. One thing we need to notice that we have to see these not as 2D lines. These are 3D planes. So over here, this is the x-axis, this is the y-axis, this will become the z-axis. The XYZ planes basically, not axis. So the velocity and direction of the winds are the net result of the wind generating forces. The wind in the upper atmosphere 2 to 3 kilometers above the surface are free from frictional effect. The surface are controlled by the pressure gradient and the Coriolis force. When isobars are straight and there is no friction, the pressure gradient force is balanced by the Coriolis force and the resultant wind blows parallel to the isobar. This wind is known as the geostrophic wind. So when the pressure gradient force is balanced by the Coriolis force, like they both cancel each other out, uh, the resultant wind blows now parallel to the isobar. So in the northern hemisphere, as we see, wind blows towards the right, and here towards the left. So the wind, which basically blows parallel towards the isobars because of the net effect of the pressure gradient force and the Coriolis force cancelling each other out, is known as the geostrophic wind. The wind circulation around a low is called as the cyclonic circulation. Around a height is known as the anticyclonic circulation. So in the low, we have the cyclonic circulation of winds. The direction of winds around such systems changes according to their location in different hemispheres. So over here at low we have cyclones, which is known as cyclonic pressure system at low pressure condition at the center. In the wind direction, basically the northern hemisphere is anti-clockwise. Cyclone at over here it will blow anti-clockwise. Whereas in the anticyclone, if there is high pressure, it will flow clockwise. In low, anti-clockwise. Just remembering the northern hemisphere. So in northern hemisphere, if there is low, then there is cyclonic. This will flow anti-clockwise. That's it. The rest other conditions can be determined after this. So similarly, in northern hemisphere, if there is high, then there will be anticyclonic conditions. This will be having clockwise pattern of wind. So the wind circulation at the Earth's surface around low and high on many occasions is closely related to the wind circulation at higher level. Generally, over lower pressure area, the air will converge and rise. So air will converge and rise over the low pressure areas. Over the high pressure areas, the air will subside from above and diverge at the surface. So air will come like this and then diverge at the surface. Whereas in convergence, the air will rise. Apart from the convergence, some eddies, convection currents, orographic uplift, and uplift along fronts cause the rising of air, which is essential for the formation of clouds and precipitation. So eddies, convection currents, orographic uplift and uplift along the fronts causes the rising of the air also. So here we have the convergence low where the air actually rises and then diverges over here, whereas where there is high over the high pressure areas, the air will subside and then diverge at the surface. General circulation of the atmosphere. The pattern of planetary winds largely depend on latitudinal variation of the atmosphere, atmospheric heating, latitudinal variation of the atmospheric heating, emergence of pressure belts, the migration of belts from apparent path of the sun, the distribution of the continents and the oceans, the rotation of the earth. The pattern of the movement of planetary winds is called the general circulation of the atmosphere. The pattern of the movement of the planetary winds is called the general circulation of the atmosphere. The general circulation of the atmosphere also sets in motion the ocean water circulation, which influences the Earth's climate. So over here we could see this representation. This is 0 degree Celsius equator. So 0 degree from 0 to 5 degree north and south. These areas basically are the low pressure or equatorial lows where there is IT season. So this is low. This is subtropical high, subpolar low, polar highs. Similarly in the southern hemisphere. So these are the pressure zones. Then about the winds. So over here at the Arctic Circle, basically we have the polar vortex. The polar easterlies originate from here. Then over here in this area between 0 to 30 degree north and south, we have the north and southeast trade winds. So the wind directions are basic. The winds are basically named from the direction they originate. Since these are originating from the east, these are northeast. They are originating from south to southeast. Westerlies will be like this. So there are different cells. This cell basically is called as the Hadley cell, then the Ferrel cell, then the polar cell. HFP. Hadley, Ferrel, and polar. The subtropical jet stream, polar jet stream. Basically, over here, because of the low pressure conditions, the air rises, and then in the subtropical high, it here subsides and then diverges over here, then rises again. From the poles, the air moves like this. This is the high basically. So here diverges, then rises, then here. So one cell is completed. So over here, the air rises, then like there is this division, then it subsides in the high, then again the division. So one cell is completed, just called as the Hadley cell. Over here, this is the Ferrel cell. Over here, this is the polar cell. So Hadley, Ferrel, and polar cells. So the air at the intertropical convergence zones (ITCZ) rises because of convection caused by high insolation and low pressure is created. The winds from the tropics converge at this low pressure zone. When converged air rises along with the convective cell, it reaches the top of the troposphere up to an altitude of 14 kilometers and moves towards the poles. This causes accumulation of air at 30 degree north and south, therefore subtropical highs. Part of the accumulated air sinks to the ground and forms a subtropical high. Another reason for sinking of the cooling of air when it reaches 30 degree north and south latitudes. Down below, near the land surface, the air flows towards the equator as the easterlies. So down below near the land surface, the air flows towards the equator as the easterlies. So here, the northeast trade winds, the easterlies, the north and southeast trade winds. The easterlies from either side of the equator converge in the ITCZ, intertropical convergence zones. So circulations on the surface, upwards and vice versa are called cells. Such a cell in the tropic is called the Hadley cell. In the middle latitude, circulation is that of the sinking cold air that comes from the poles and the rising warm air that blows from the tropical high. At the surface, these winds are called westerlies and the cell is known as the feral cell. So these are the westerlies and this here is the feral cell. At polar latitudes, the cold dense air subsides near the poles and blows towards the middle latitudes as the polar easterlies. This cell is called as the polar cell. These three cells set the pattern for the general circulation of the atmosphere. The transfer of heat energy from lower latitudes to the higher latitudes maintains the general circulation. The general circulation of the atmosphere also affects the oceans. The large-scale winds of the atmosphere initiate large and slow moving currents of the ocean. Ocean in turn provides input of energy and water vapor into the air. These interactions take place rather slowly over a large part of the ocean. So this paragraph is about the ENSO El Nino Southern Oscillation. So the warming and cooling of the Pacific Ocean is most important in terms of the general atmospheric circulation. The warm water of the central Pacific Ocean slowly drifts towards the South American coast and replaces the cool Peruvian currents. Such appearance of warm water off the coast of Peru is known as the El Nino. The El Nino event is closely associated with the pressure changes in the Central Pacific and Australia. This change in pressure conditions over Pacific is known as the Southern Oscillation. The combined phenomenon of Southern Oscillation and El Nino is known as ENSO. In the years when ENSO is strong, the large scale variations in weather occur over the world. The arid west coast of South America receives heavy rainfall. Drought occurs in Australia and sometimes in India and China. This phenomenon is closely monitored and is used for long range forecasting in major parts of the world. So basically what it means to say is that if this is the coast of Peru, this is basically a semi-arid region. So in the El Nino, basically the warm ocean currents replace this one. Now here it has the warm ocean currents which then rises and forms the moisture and then rainfall appears in the coast of Peru, higher rainfall. Whereas in Australia and some parts of China and India, there is drought. This condition is known as El Nino. In simple terms, there are water circulations also associated with it. Then there is El Nino Madoki. So we've come to an end to this video. It's been a totally hectic video. I'll see you guys in the next one where we revise the other concepts related to geography and just finish off this very book in the upcoming videos. Till then, see ya, bye, and all the best for your upcoming examinations. I hope all of us do well.